ready for this one?
Yeah, you can use mine.
Okay. So I try to dress a little bit better. Don't feel nervous and just share your thinking. Can you put your So you do have something fresh to share with people here, and so it's still an ongoing effort, and so we just wish the minimum requirement is you can identify something that you believe is publishable, and you and your advisor believe is publishable. I think that's already a goal we achieve. So.
This one?
Okay. Who's coming? Okay. Yeah, excellent. So our next presenter is our master student Marwin and a bachelor degree holder in bioengineering and switched to mechanical engineering and doing fractional mechanics. I believe it's the right combination. So, your time.
Okay. Hello, everyone. So today I'll be talking about fractional analysis of time voltage area of an EKG. So the motivation behind my this research is that there's a particular paper that examined the area, particularly in these areas of the EKG, and what they found from calculating these areas was that it's related to how hard your heart works. The bigger the area, the harder your heart works, and what they found from the calculations was they were able to prove LVH, which is left ventricular hypertrophy, which is essentially when your left ventricle thickens and it works harder. The reason why this is important is because that chamber of your heart is actually responsible for the blood flow pumping to the rest of your body. And some background information. So a lot of fractional analysis has been done on the RR interval, or I like to say heartbeats, because the peak of a heartbeat is essentially just these little rectangles. And you can see from these rectangles that they actually say more than that. They actually say within that rectangle, you get an EKG, actually. So when a doctor says, oh, you have 60 beats per minute, that doesn't necessarily say anything about your fitness or health to any degree. Now, if he can tell you the area under the curve per beat for the interval, then that would be a little better, because then he could tell you if you have an enlarged heart or not. So. And so just a little more background information, because I'm going to be covering the EKG in very high detail, so I want to be able to let you guys understand the electrical conduction of the heart. So what happens is it starts with the SA node, and this is basically the pulse generator. And originally I was going to do a fractional model of a heart, but it's already been done. So, and they mapped it out very nicely on a circuit as well with chaos theory. So, but going on, this SA node essentially has electrical conduction that goes around the atriums, and the atriums are the two top chambers of your heart. And that's responsible for this P wave. And as it goes down, it goes to the atrioventricular node, which is essentially, the way I like to see it is like a gas station, or it's more like it helps, it's another node in the pathway that helps speed up the conduction through the rest of the heart. And it's connected to something called the bundle of FISP, which is located essentially in between the left and right ventricle. And that electrical signal propagates back upwards. And that, when the atrioventricular node sends that signal down the bundle of FISP, it's responsible from the Q to the R complex. And then when it travels upward through the Purkinje fibers, which are essentially on the outer part of the ventricle, it's responsible for the R to the S portion of the EKG. And then this T is not shown. It's actually like a relaxation pulse. And so before we can do any data analysis, we need to know where we're going to get our heart data. So what I used was something called PhysioNet. And PhysioNet is a great website for getting a lot of EKG data. The three main sets that I looked at were from mainly MIT and Boston Institute of Health for normal and arrhythmic and sudden cardiac death. And they also provide toolkits, but the toolkits, some of them do not work, or maybe I couldn't get them to work. But the one thing that did work, that John helped me out with, was that using the data I did have, I could use the rdata.m to convert the files into something I could read. So I was able to get that going. And then just so I run down how I actually did my procedure, was that I essentially ran the EKG, and it was 1 minute per set, and I only did 1 minute, even though hours were provided, is because what I'm doing is, the reason why it's innovative is because the software to get bigger data sets is not available. So that's something I'm trying to work towards, and I'll explain that more later. And essentially, I use the, in order to get some area, I use a baseline under the EKG. And I use 0.8 millivolts because that's actually the resting potential for the heart. And if it goes higher, if it goes below that, it actually activates the Purkinje fibers to create a heart signal or impulse as well. So when you go below a certain threshold, it's going to cause arrhythmia or irregular beats. So I just set that as the baseline. And then I manually calculated, or I found the peaks through graphs. Each data set was about 100 points, which wasn't enough when I got the results, but I'm hoping to work towards bigger data sets for this research. And then I ran the two Hertz estimators that essentially did not give me crazy results, and they were consistent for the most part. Just get some more. Sorry. So once I run the EKG, and this is for less time, this is just an example until I get to the real data, because it's very dense. So This is from someone that has arrhythmia. It doesn't seem like it, but that's why I'm going to try and calculate some area under the curves to hopefully be able to say something about this person's HRV or EKG. And essentially, the next part, I take the baseline, which is 0.8 millivolts, and I basically, this is just to show the user on the program that this is like the area of interest that we want. Now, in the next part, this is, I think, the innovative part, but it needs to be automated or coded better. And what I do is I manually go in the graph and I take each R point, and then from there, it essentially lets me graph from that point to that point the area I want. And then I shift it, and then I keep doing that, and I did that for 100 times for each data set. So, and no one's ever done this because it's kind of slow, and there's potentially, it's just very slow. So this is very new. If it can be automated, this has high potential for some very promising research. And what the reason why I do this is also that because I use Hurst estimators, and periodicity is not Hurst estimators' friends, and the information the Hurst estimators spit out from periodic time series aren't that promising. So what I get from this is time series that I can actually use for the Hurst estimator, and that's what I do. And I basically use the Hurst estimator that was from the lab 3 in this class. I mainly use the RS. It's the most commonly used one from a lot of research articles that I've read. And then the aggregated variance method. It's also called the time variance method in the graphs listed, because that's how the graphs are labeled from the user. And then, so for the Hurst estimator, from a couple articles that I've read, they do say heart rate variability has long range dependence, but a lot of times they only read the RR interval, and that's just let me see if I can go back. It's just this distance, but this distance doesn't really tell you much, because if you remember in the beginning of the slide, that's just like saying, oh, that's just the space between your heartbeat, which I personally don't think means too much, and they haven't found any significant data. So yeah, so I'm back, and then so I'm giving the Hurst estimator data that it can actually use, and then like I said before, I'm using the areas so that the Hurst parameter is not really I can use this data because it's not periodic, and for Hurst, oops, if you're under 0.5, it's not trending towards a persistent, I guess, like trend. And then when you 0.5, from what I've read from articles, it's just randomness, like it's not correlated. And then from what I read from articles, if you're greater than 0.5, it trends to persistent, or it's like positively autocorrelative, and we'll go into like what that means for these data sets. And I know I'm running out of time. So really quick, 1 minute were used, 3 EKGs were read. one thing I have to note ethically, the normal sinus rhythm data will not compile from the code the PhysUnit gave me. So I actually used arrhythmia data set for this normal sinus rhythm, which I had to do, but I double checked the person that I grabbed the data from, and the data, the person exhibited normal sinus rhythm, and I took the data set from that episode of the normal sinus rhythm. So just to let you guys know that. And then, so these were the data sets used. That's a lot of data. I calculated each peak. This was the person that had the arrhythmia, but they this was during their normal sinus rhythm. As you can tell from the beginning, it doesn't look too normal, but that was the best one that I could find. For the arrhythmia, this person definitely had arrhythmia, and those are going to give a lot of different areas. So hopefully we can figure out something from that. And then this person died from a sudden cardiac arrest, but not in the first 60 seconds of the EKG, but it's showing some big QRS over in this area. And it actually, this became a little subjective because the R interval from that was not, it activated the Purkinje fibers that had another beat. So I had to put that into consideration. And then, so this is the normal sinus rhythm. And then I'm going to go over the FISP parameter meanings because I'm running out of time. I have them all in a slide together. And then this was the arrhythmia data set. And then this was the sudden cardiac death data. So from the normal sinus rhythm, it was the only data set that gave me 2 different values, and this could have been because of that there wasn't enough data, or some human error, because I manually calculated everything. But the arrhythmia and the sudden death were both consistent in their values for both the time variance method and the RS method. And they both, I guess, sorry, just. And what this is saying to me is that for the Hurst estimators is that like the arrhythmia and the sudden death, they're corresponding to these trends, and I'm assuming that these trends are the irregularities in the EKG, and they're essentially predicting that they're going to happen again. And they do. I sampled them for a lot longer, and I do see the trends, especially with the sudden death. But the sudden death, I couldn't find where the person died because that was a big data set. And in conclusion, the normal sinus rhythm, I didn't find the results, I guess, conclusive enough, and I think I just need more data to run, or I need to double check if I made an error, because that was the last data set I made. And then for the arrhythmia, definitely it's, the Hurst parameter suggests that it's trending towards some persistent behavior, and I noticed that the person is experiencing a tachycardia, and you can, if you spread out the EKG, you can actually see bits and pieces of those persistent trends. And for the cardiac death, there's those big peaks, and they're pretty erratic, but the Hertz parameter suggests it could be trending towards those erratic EKG signals. And then definitely need more data. For the future, I hope that I can code for something that can calculate those peaks, but I couldn't find anything that would calculate the very top of the peaks for the EKGs, and manually doing it wasn't realistic because I think you need like thousands of like data sets because it's long range dependent and you need big data if you want to say something about it, the data set. And troubleshooting the PhysioNet data converter so I can get the normal sinus rhythm to work. And then test out the other Hertz estimators because the graphs and the values were all skewed because there's 100 data points. I don't think is enough for a Hertz estimator. So, and then thank you. And questions?
Good. Questions? Actually, I expect to see. Okay, go ahead.
Do you have any sort of range of the Hertz primary series original versus FISP or some kind of that?
No, I think I can give you a more definite answer if I had more data, because even though it was innovative that I could take each interval and make a time series and run it through the Hertz, it just wasn't enough data for me to say anything really. So, and I'd like to see how the other Hertz estimators actually run as well. So.
Okay. So actually, the real problem here I see is using RR interval is not as good as using the difference of the area. Okay? So the area is adding together, and you do the difference, you get the time. So the time series you made was manually did?
Yeah.
Do the area?
The code.
The difference of the area?
There was like 3,000 lines of code.
Did you do the difference of the area?
Yeah, like for the top and the bottom, or like the
difference between two beats, the area.
No, I just did. Yeah, the difference.
Yeah, you have to use the difference so you can pull out that what we call variability. HRV, V stands for variability. So those fractional dynamics were embedded into this variability. So whenever you see fluctuation or variability, think about fractional mechanics. So we most likely we can pull out the data and take a look at this first round. And those first rounds could tell us what kind of disease the patient may have. So there are some specific indicator to for using a first round to indicate the course, different conditions of the body. Okay. So the philosophy is clear. Whenever you have a signal that is derived or observed from a very complex system like a human body, so physiologic signal, then that signal must be lumped lots of internal dynamics and to reflect into this as fractional dynamics. Those fluctuations must contain fractional dynamics. There's a chance you can explore the beneficial use of fractional dynamics. That's almost sure. Like social data, a lot of things you have heard enough from me. So today, this is just an example. Our next example would be a puzzle. You will see something interesting. So let's thank Marwin. Oh, you have a question?
Yeah. So for the healthy person, to
theoretically, what should be the hash estimator?
Well,
There isn't a definite value because different people with different conditions, different health conditions.
So, my question is,
There isn't a definite range.
for a healthy person, the heartbeat, the graph should be just repeated and repeated with no significant variation. Because I saw in the ones that they have problems or they have heart attack, there was something like a big change or something that we could figure out, or that caused the hair estimator to be something else rather than the normal default data we assume. So I was just wondering if there is something we expect theoretically to see from a healthy person. The value of hair estimator.
I need more data. I mean, I want to say,
What do you think theoretically?
Theoretically.
Not thinking about the data. Should it be 1?
I think it's more close to 0.5, right?
yeah,
This is a very good question, but I have my understanding. So, Bruce West said that the reason you are still alive is because you have fluctuations or variability maintained that level. If your variability is flat, you're not dead. So, right? So that means the variability is high, means you are more healthier. So from that point of view, then we can plan that this is a physical basis of you are supposed to see the difference from first anti-persistence or persistency.
So
I think personally 0.5. I think it's going to be the just random. Just yeah, that's.